Well, would you like to do the honors and introduce our speakers?
Okay. I made up some copies. There are 8 here, which is not enough for all these people, but you can hand them around and look at them. Let's just disperse these.
Okay.
There's some pretty pictures in the back. The list of publications on the back is just there because it was the easiest thing to print that page. That is far from complete. The curriculum vitae is so long that I was too cheap for paper.
No.
Carter Hall received his BS degree summa cum laude. At Columbia, they didn't use the Latin. So mine says with highest honors in physics. I don't get the summa cum
Well,
laude.
either way, you're introducing Carter.
I feel shit. Anyway, that was from Virginia Tech, and PhD from Harvard University, where he was awarded the Goldhaber Prize and the Wallace Noyes Fellowship. After his postdoctoral appointment at the Stanford Linear Accelerator Center, he joined the University of Maryland as assistant professor in 2006. He received the Department of Energy Early Career Award and what's a CMNS? You know what that is?
Oh, that's our college. College of Mathematical and Natural Sciences.
Dean's Award for Excellence in Teaching. He teaches. His research is on the border between nuclear and particle physics. I don't quite fathom that. Okay. Including the EXO experiment seeking marijuana neutrinos and the Lux
Marijuana neutrinos.
and LZ experiment searching for weakly interrelated matter, which you talked about here.
He came to an unfortunate end.
Can I use that one?
Yeah.
The marijuana neutrinos, can I use that?
The pretty pictures are some of the apparatus that you'll see. I thought you might like to take them home. You know, I'm 82 now, but it seems to me that the younger generation of physics must be sterner stuff than my generation. Jack and Wayne and I heard a talk on the optics involved in the gravitational wave experiment, and man, that was hard.
Complicated
And
stuff.
this is
I didn't
hard.
understand it.
To have done such an experiment in a whole, anyway, he'll tell you about that. It really must take some courage. So I give you Carter Hall.
Okay, well, thank you for that kind introduction. So, yeah, I'm happy to be here. And,
Question.
Yes,
Is the Goldhaber Prize Maurice Goldhaber or Gerson?
it's Maurice, yeah. So I'm happy to be here, and let's see, I was going to make some comment here, but now it's escaped my mind about the background here. Anyway, I've been here at the University of Maryland, been local in the DC area for 10 years, and yeah, I've been working on this dark matter experiment since 2008, so about 8 years. So I'll be happy to tell you about the results that we have from our current experiment, which is the one that's pictured here. That's the detector. And I'll tell you a little bit, very, very briefly at the end, about the next experiment that we're intending to do, which looks a lot like this one, just larger. So this is underground in South Dakota. This is in the former Oklahoma State mine in South Dakota.
About a mile underground.
It's about 1 mile underground.
Yeah,
That's
yeah.
right. So we're looking for cosmological dark matter, and the idea is that the dark matter, most hypotheses are that the dark matter should be, present here with us in the room. We don't know what it is, but there's lots of astrophysical evidence for its existence, and most of that evidence points to it being kind of a semi-uniform soup, and I think this is the point that we'll talk about here in a moment. So most hypotheses for what the dark matter is that it's made of particles, although there are alternative hypotheses that maybe the dark matter is an effect of a gravitational law that we don't understand. But in our experiment, what we're doing is we're kind of looking for we're following up on the particle hypothesis, and we're kind of looking for those particles locally here with us. The idea is, well, if it's really true that the dark matter is made of particles, and if it's really true that there's a uniform soup that our galaxy is immersed in, then perhaps we can build a detector, a somewhat traditional particle physics detector or a nuclear physics detector, and try to detect those particles locally here with us. So the evidence for dark matter is that there's a wide variety of astrophysical evidence, all of which goes back to its gravitational interactions. We've not seen dark matter in any way except through its gravitational effect on ordinary matter. One famous example of the dark matter phenomenon is the rotation curve of a galaxy, that is the velocity at which the stars in the galaxy orbit the galaxy or rotate around the galaxy. as a function of their distance from the center of the galaxy. So we were discussing this plot at lunch. You can see that that if there was if the gravitational force that these stars are experiencing is due to nothing but the visible matter, then you would expect the velocities to be dropping as you go further out, because the visible matter is so concentrated in the center. And what's actually observed for hundreds of galaxies, but essentially every galaxy for which this has been measured, is that you don't see this drop off that you would expect from the visible matter. Instead, it kind of rises or perhaps becomes flat. And the discussion we were having at lunch was, given if it were just perfectly flat, which is not for this particular case, but if you had a galaxy where it's perfectly flat, what is the dark matter distribution, density of the distribution that you would need to explain that based on ordinary sort of Newtonian or Einstein gravity? And so if the velocity distribution is perfectly flat, and this is what we were discussing at lunch, it's true that you need a dark matter distribution that prefers to be in the center and kind of falls off. That is what would make the velocity distribution flat. What we actually see in most galaxies is not truly a flat distribution, but kind of a slowly rising distribution, and this is what's more consistent with kind of a uniform suit. Although that's a rough statement also, because it is true that in most galaxies, what we see when we analyze these curves is that there is an overabundance of the dark matter near the center of the galaxy, and then it becomes kind of a more uniform suit further out. Okay? And there's debates about the exact shape of what it looks like in the very center of the galaxy, whether some simulations indicate that it should kind of have a cuspy profile where the density keeps going up as it intersects r equals 0. Some indicate there should be more of a kind of a spherical, soft profile in the very center. So these are questions of current research. But just the fact that it's not following what you expect to see from the visible matter alone is one indication that we take for the existence of the dark matter. Another indication is from galaxy cluster collisions. This is a famous example. This is the so-called bullet cluster. In this picture, 3 different instruments have been combined together, or 3 different data sets, so to speak. There's a visible picture where you see all the optical picture that you're seeing here. The red is X-rays from hot gas in the hot gas that's in between all the galaxies. And then the blue glow is the inferred location of the mass of this system as measured through its effects on gravitational lensing. So in other words, by looking at these background galaxies and searching for the very small effects of gravitational lensing, these astrophysicists infer that most of the mass is where the blue sections are. And this is a famous example because it apparently shows that the ordinary matter that's mostly made up of this hot gas, which is the red, is, in this case, apparently physically displaced from where the gravitational mass is. And that's usually taken as strong, compelling evidence that the dark matter is some sort of particle thing that is very non-interacting. What we think has happened here is that these 2 galaxy clusters, what has happened here is that these 2 galaxy clusters have collided. The ordinary matter, being made up of atoms, has, when it collides with itself, of course, it heats up and slows down. And so the ordinary matter has kind of been left behind, but the dark matter is apparently kind of ballistically went through without interacting very much, and is now separated from the ordinary matter. Another famous example, and in my opinion, probably the best evidence for the existence of the dark matter is the anisotropies that we see in the cosmic microwave background, as well as its overall smoothness. I'm going to make a couple more comments about that.
Question, please.
Mm-hmm.
On that rotation curve plot you showed, is it possible to infer a velocity distribution from dark matter?
So from these observations, it's not possible to infer the velocity distribution. Of course, what we do know is there's constraints on it, of course, because the dark matter needs to be gravitationally bound to the galaxy, and so it cannot be too fast, for example, because it would have escaped the galaxy long
Cold
ago.
dark matter.
In particular, cold dark matter, but any dark matter, if its velocity was too large, it would just escape the gravitational potential of the galaxy. So the fact that it remains present today, means that that places an upper limit on what the velocity can be for those dark matter particles. Another thing we can say is that if you take a dark matter particle that's located at a particular point, like where that particular star is, its rotational, its orbital velocity, it should be experiencing the same gravitational force that the star is experiencing. Therefore, we expect that its typical velocity is kind of typical of stars at that point. So by measuring the orbital velocities of the stars, we infer that the typical velocities of dark matter particles are going to be similar because we're hypothesizing that they're experiencing the same gravitational force that the stars are seeing. Okay. Yes.
The thing I saw in the paper the other day that they think there might be 10 times as many galaxies as they thought before? Does that affect the bottom curve, or does that affect anything about dark matter?
I don't think there's any direct consequence for dark matter. I think that I saw that article in the paper. I believe it was about galaxies that are. Was it because they were hidden from view previously, or because they're in the very, very early universe?
I think they're early universe.
Yeah, I can't comment directly on it. I can't comment directly on it. It is true that by looking very far back in time, seeing the proto-galaxies that were present, 1 billion years after the Big Bang, that provides evidence for the nature of the dark matter, that the dark matter has to be cold, because you can kind of see the galaxies assembling as you go forward in time when you look at, say, the Hubble Deep Field, and the fact that galaxies today assembled from smaller galaxies is in fact further evidence for the existence of dark matter. But this particular result that was in the paper last week, I can't really comment on it. Yes.
How much denser in dark matter do you assume our local environment is than the intergalactic mean given by that pie chart?
Yeah,
100
that's
times denser.
a good question. So so the local dark matter density is overdense compared to say intergalactic space or intergalactic mean. And the ratio off the top of my head, I can't tell you with confidence. But it's true that earlier in the universe, of course, things were much more uniform. Today we have these gravitational potential wells that the dark matter and the visible matter have fallen into. So it's true that we're living in in modern days we have an overdensity compared to the average density. The exact ratio I can't tell you off the top. Okay, so when we look at the universe today, we do a galaxy survey, for example, like the 2-degree field, the Sloan 2-degree field. We can make these diagrams where we plot the locations of the galaxies. So every dot in this plot is an individual galaxy. There's over 2 million galaxies shown here. What we can see is that the galaxies are clustered along these filaments that are overdense with ordinary matter and presumably with dark matter as well. They are overdense with dark matter as well. And then there's these kind of voids, these bubbles where there's not much matter and not much dark matter either. So today's universe is clustered and not isotropic. It's not uniform. We have these grand overdensities, grand underdensities. Of course, when we go back in time and we look at the cosmic microwave background, which is a picture of what the universe looked like when it was 380,000 years old, at that time the universe was extremely uniform. The cosmic microwave background is famously uniform. Its variations are only 1 part in 10 to the 5. And so the question that we have is, how do you get from this extremely uniform soup of matter when the universe was 400,000 years old to the extremely non-uniform universe that we see today? We know that the universe is 14 billion years old, so you've got 14 billion years to get from this extremely uniform state to this non-uniform state. And so, of course, it's gravity's job to do that for us, and there's simulations that show that happening. So this is a simulation that shows going from a uniform soup into the filamentary structures that we see today. It's a gravitational simulation. The interesting thing here from the point of view of dark matter is that if it was only ordinary matter that was creating the gravitational potential wells, then starting from this uniform soup, it's not enough time. 14 billion years simply is not enough time to get these grand overdensities and underdensities that we see today. So it's necessary to have. It's necessary that back then there must have been gravitational potential wells that the ordinary matter was going to fall into over 14 billion years. Those gravitational potential wells need to have already existed at that time in order to get the structure that we see today. And our inference from that is that the dark matter was there at that time and it was already clustering itself. Although the ordinary matter was too hot at that particular moment to have fallen into those potential wells yet, that the dark matter is already there and already creating these gravitational potential wells, and that's seeding this galaxy structure formation. So this paradigm kind of came about in the 1970s and 80s, and this is called the cold dark matter paradigm, that we need something to seed these galaxy structures. Yes?
Yeah. The video that you just showed, was that assuming that the cold dark matter
Yes.
started?
Yeah, so this particular simulation has cold dark matter in it, that's correct.
Can you run it again?
Sure.
That would imply then that cold dark matter interacts, is self-interacting, even though it doesn't interact with ordinary matter?
Well, so the cold dark matter is it's not necessarily very interacting with itself very much, but it is, because it's cold and it's very slowly moving. It's able to fall into gravitational potential wells and reinforce those potential wells while not sort of escaping and smoothing things out. An example, the reverse example, the alternate example, so-called hot dark matter, of which neutrinos are a famous example. Neutrinos being so light, being so ultra-relativistic for any velocities that we can imagine being present, neutrinos are extremely relativistic. So they have the opposite effect of smoothing out gravitational potential wells because they escape the gravitational potential wells, and so they have the effect of filing off the rough edges and making it a very, very uniform soup. So neutrinos have the opposite effect. What we need is some form of matter that is heavy enough, that it is non-relativistic enough that it's able to fall into these potential wells and reinforce them. Okay. So this is a picture of the anisotropy in the cosmic microwave backgrounds. This is what you see when you look at the cosmic microwave background with great contrast enhancement. These fluctuations from the red to the blue are fluctuations in temperature and in density of 1 part in 10 to the 5. And so we can see these with modern experiments like the Planck experiment, which took this picture, took this data. And so it's these little spots here, and the red spots and the blue spots, so to speak, that represent the overdensities and underdensities at the time that the cosmic microwave background was released, 400,000 years after the Big Bang. And when we look at the, if we take a Fourier transform of this picture, or decompose it into spherical harmonics, is another way of saying it, what we're going to see is we're going to see lots of power present in the Fourier transform on scales that are kind of typical of these dots that you see. That scale is about 1 degree. So when we take the Fourier transform or decompose into spherical harmonics, we do see this great power peak at about a 1 degree angular scale. We also see these other peaks that are kind of acoustic peaks. They represent, this represents structure on the scale of 1/2 degree. This represents structure on the scale of 1/3 degree, etc., 1/4 degree, 1/5 degree. And what's being represented here is that in the early universe, if you had a size of space that, from our perspective today, looking at it, would subtend about one degree on the sky, that's the volume of space which had time in 300,000 years from the start of the Big Bang, or from the start of the expansion of the universe, until when the cosmic microwave background was released. That's the size of space that had time to collapse once. That is, if you had a little bit of overdensity in the very initial conditions, that volume of space was able to collapse once. That's why you see lots of dots of that size in the cosmic microwave background. Smaller regions that are on the scale of 1/2 degree, regions of that size had time to collapse once and then heat up and rebound once. So what you're seeing, why we see power at 1/2 degree scales, because that's the volume of space in 300,000 years that had time to collapse once due to gravity, heat up, and then re-expand. And similarly, we have all these other acoustic peaks. Each one is just adding on one more process to that sort of acoustic process where you collapse, rebound, collapse, and rebound. From the point of view of the dark matter story, the really interesting thing about this power spectrum is that this third peak is just as prominent as the second peak. And what this is indicating is that, well, I should say, if there was nothing but ordinary matter present, we would really expect this third peak to be suppressed compared to the second one, kind of like the fourth and fifth and sixth ones are. The reason being that if matter collapses and then re-expands, if it's going to recollapse again, it's the gravitational force that's driving that collapse. But once it's re-expanded, it's now become more diffuse. And so restarting the collapse process, that can happen, but it's a little bit difficult to get it started, because the whole point of what happened in the expansion, of course, was that it became uniform and the gravity then got spread out. So the gravitational potential wells got kind of smoothed over. So the fact that this third peak is so prominent compared to the second one is indicating that when the ordinary matter bounced back and expanded, there was some portion of the plasma, some dark matter portion of the plasma, that did not rebound and expand. It just continued to fall in and continued to reinforce those gravitational potential wells. Then that large gravitational potential well was able to draw the ordinary matter back in. So this is the really remarkable thing about the cosmic microwave background, and we're fortunate to live, it's remarkable that we live at a time when it's possible to make a picture like this, where you can image this kind of microphysics, this kind of microplasma physics with such detail, and fit it to a theoretical prediction that only has 6 free parameters with such good results. So this is, in my opinion, this is sort of the single if you had to point to one single piece of evidence for the presence of the dark matter, the existence of the dark matter, I think this is the one you would probably point to. So we need some sort of matter that is mostly non-interacting. That means it should be electrically neutral, should not be made of atoms, should not be made of protons, neutrons, and electrons. When we look at the fundamental particles that we know of course, we do have neutrinos. They sort of fit the bill. They're electrically neutral, of course, so in that sense they form dark matter. And in fact, of course, we know neutrinos exist. We know that they were present in the early universe, so it's undeniable that neutrinos make up some portion of the dark matter. However, they're not the dark matter that we're looking for, per se. The problem is that they're not heavy enough, as I mentioned, and so they tend to smooth out these the gravitational potential wells as they escape from the gravitational potential wells. So what we need is kind of something like a neutrino that is neutral but heavier, so that it's not so relativistic. And so what we can just sort of generalize a neutrino. We can kind of picture some other particle that's not yet been discovered. We would call it a weakly interacting massive particle, and very crudely speaking, we can kind of think of it as like a neutrino but much heavier, so that it's moving slowly and can fall into a gravitational potential well. So we call these WIMPs. So this is sort of one of the main paradigms, through which people think about the dark matter problem. So, given that dark matter exists, we can now ask the question, well, if dark matter is existing, we know it interacts gravitationally with ordinary matter. We know that it doesn't have strong electromagnetic interactions with ordinary matter, nor strong nuclear interactions. So it's mostly standoffish from ordinary matter, not interacting with ordinary matter except through gravity. On the other hand, we can imagine that there is some weak coupling between these two forms of matter, and particle physics theories would indicate that that's a reasonable hypothesis, that there might be some sort of non-gravitational interaction between the ordinary matter and the dark matter. So if that's the case, then we can think back earlier in the universe and ask, was there a time in the universe where the dark matter was actually a participating part of the plasma, was not standoffish, but was in fact interacting with the ordinary matter? And the usual paradigm for thinking about this is to think about when the universe was, say, maybe a nanosecond old. Back then, the temperature of the plasma was like 100 GeV. And if we have dark matter present and also ordinary matter present, we can hypothesize that maybe there's some sort of scattering interaction between the two. And if that was the case, then when the universe was hot enough, when its temperature was comparable to the mass of the dark matter particle, then there should have been two processes going on. There should have been dark matter annihilation going on, like this, producing ordinary matter. And as well, there should have been ordinary matter colliding to make the dark matter. So we should have both dark matter creation and dark matter annihilation going on at this time in the universe, under this hypothesis that it does interact somewhat with the ordinary matter. So as the universe ages a bit, once it's no longer a nanosecond old, but once it's a microsecond old, say, its temperature is cooling down. At some point, the temperature is such that the creation process is no longer kinematically allowed. So that the ordinary matter no longer has enough kinetic energy to create the dark matter particles. And when that happens, the dark matter is going to continue to annihilate into ordinary matter, but it's not going to be created, and that means that its abundance is going to start to drop. And as the temperature of the universe drops further and further, the abundance of the dark matter should drop further and further. Eventually, however, another process will take over or start to dominate, and that's the expansion of the universe. At some point, the annihilation process is also going to stop, just simply because the universe is expanding fast enough that the dark matter particles simply can't find each other to annihilate anymore. So they'll become dilute enough that the annihilation will also turn off. And at that point, we would expect a constant abundance of dark matter to be present. And so that whole story is kind of represented by this plot. The time on this plot is on the upper axis here. This is in nanoseconds, so 1, 10, 100, and 1,000 nanoseconds. The y-axis is the dark matter abundance. We're going to hypothesize a particular dark matter mass, particle mass, say 100 GeV. And as time goes forward, the universe is cooling, so the dark matter abundance is going to start to drop. And then as the expansion starts to win out, eventually the dark matter is going to become of uniform abundance in an expanding volume of space, which is what's being plotted here. So how much dark matter is left over is kind of represented by these various different colors here. It's possible that if the annihilation cross-section is fairly small, then we'll be left over with a pretty high, fairly high dark matter abundance. So the abundance is plotted on the y-axis over here on the right-hand side. This very upper curve would represent 100 times the critical abundance of the universe, or critical density of the universe. On the other hand, if the annihilation cross-section of dark matter is very, very large, then there's going to be less of it left over. So the relic density that's left over is going to be much less, maybe some tiny fraction of the critical density of the universe. Now, of course, we've measured with techniques like the cosmic microwave background. We know the density that the dark matter represents. We know that it should show up right here. So that's the correct one that we observe in the sky. And so this argument is saying that if you're going to assume this thermal hypothesis that the dark matter was participating in the early universe plasma, and you're going to reproduce the abundance that we see today, the argument is that this now tells us what the annihilation cross-section of the dark matter should be. Yes?
Why shouldn't it continue to go down as the universe expands?
It's just a question of the precise quantity that's being plotted here. What's being plotted here is sort of a number density as a function of an expanding volume that's expanding with the universe. So if we plot it as a function of a simple, say, liter, it would be dropping as the universe is expanding. But what they're plotting in this particular plot is the number of dark matter particles per volume of space that's expanding with the universe, so that effect is taken out of the plot. Okay? So this argument is that since we can observe the correct dark matter abundance, if we're going to assume this thermal hypothesis, then this tells us what the dark matter annihilation cross-section should be. Then it turns out, and this is kind of what seems like a coincidence, or perhaps it's a hint, that the annihilation cross-section that you need to make this relic abundance correct is typical of the weak nuclear force cross-sections, for example, cross-sections of neutrinos. So the fact that this cross-section turns out to be similar to one of the 4 fundamental forces that we know seems to be some sort of hint, perhaps, that these dark matter particles may have these weak nuclear force interactions. And that gives us some hope that we might do a somewhat traditional particle physics experiment to look for them today. Okay? So this is sort of the picture that we're working on. This is an artist's conception of a galaxy, like the Milky Way galaxy, with the stars here in the plane. And then we have this picture that there's this soup of dark matter particles that's extending far beyond where the visible galaxy is. And we're just immersed in the soup, and it should be right here in the room with us. We know that it's the typical orbital velocity of the dark matter particles that would be here in our neighborhood of the galaxy should be similar to that of our sun's orbital velocity around the center of the galaxy, which is 230 kilometers per second. So that kind of gives a scale for the velocity of the dark matter particles that we think would be present with us. That's a non-relativistic speed. It's 0.1% the speed of light. We know from the astrophysics what the mass density, the mass density of this stuff should be. It should be about 300 proton masses per liter of space. So if you hypothesize that the particle mass is maybe 100 GeV, that's telling you that in 1 liter of space there should be about 3 dark matter particles on average. Of course, the number will change then as you change the dark matter particle mass hypothesis. But at any rate, we're looking for something that's like 300 proton masses per liter. Okay. So if we think back to this thermal hypothesis, which is the standard one that's sort of the most generic one that people tend to work on, although there are other models of dark matter which are non-thermally produced and perhaps not interacting with the weak force at all. But this is one of the most common models that people that people work on and think about. It's nice that this early universe physics constrains for us what this dark matter annihilation cross-section could be. One reason why this is nice is because since the dark matter is now overdense within our galaxy, that is, it's not the uniform density that you would get if you averaged over the entire universe, but instead the dark matter has clustered into these gravitational potential wells, so we are in kind of a local overdensity of dark matter. If this annihilation process is possible, then the dark matter should have started to re-annihilate kind of recently in the universe's history. So this gives us some hope that perhaps if we look up at the sky, maybe we can see dark matter annihilation happening today. It would be essentially the same process that had happened in the early universe, but it just would have restarted at kind of a small rate recently, since the dark matter is now somewhat overabundant again and can kind of start to find itself and start to annihilate itself again. Yes?
Since we see very little normal matter annihilation because normal matter predominates greatly over normal antimatter, could there be a similar phenomenon for the dark matter?
So, right. So I think the question is, one way to state the question is should dark matter be Majorana particles, which don't have a charge, which carry no charge?
Baryon number.
Yeah.
Something like that.
Something like a baryon number, but does the dark matter carry any charged quantities at all, right? Any quantum numbers, any additive additive quantum numbers at all. And so there's different models of dark matter. Most dark matter models for the WIMP hypothesis is that the dark matter should be Majorana, meaning that it's not carrying any conserved quantum numbers, and so it's able to annihilate with itself without any problem. Yeah. But there are other hypotheses for what dark matter might be that include things like that. So if we look up at the sky today, it's possible we might hope to see this dark matter annihilation process going on, and that's something that's done typically with gamma rays, but also with charged particles like positrons, for example, and antiprotons. So if we look at the gamma ray sky with the Fermi telescope, for example, we can look perhaps for dark matter annihilation happening in the center of our own galaxy. It would look like an excess glow around the center of the galaxy, for example. We can look at neighboring galaxies that are close by but dominated by dark matter and see if we see any excess gamma rays from those galaxies. The Hawk experiment is another gamma ray experiment. It looks at very high energy gamma rays. It's a ground-based Cherenkov array. It's located in Mexico. This experiment is able to look at the sky at TeV gamma ray energies. I'll comment on it a bit because we do have a group at the University of Maryland that's one of the leaders of this experiment. They recently, well, a couple of years ago anyway, published a paper where they calculated their sensitivity to high mass dark matter annihilations. And this is one of the results from their paper. If you put the dark matter particle mass on the x-axis, this is in units of TeV, so they're looking at very high energy gamma rays, 1 TeV, 10 TeV, 100, and 1,000. On the y-axis, what they're plotting in these various curves is their sensitivity to the annihilation cross-section. Now, the correct thermal cross-section, the one that you need for this thermal dark matter hypothesis, is down here. It's this horizontal line. It's about 2 or 3 times 10 to the minus 26 in these units. And what they have published here is that if they look at nearby galaxy clusters like the Virgo cluster or the Fornax, M31, nearby Andromeda galaxy, and other things, they expect to be sensitive after 5 years of data to cross sections that follow these curves as a function of the dark matter mass. So for these scenarios, their sensitivity is going to be maybe a factor of 1,000, 10,000, 100,000 less than that which is necessary to see the thermal dark matter annihilation cross section. So now, we don't know that dark matter is thermal, so this thermal annihilation cross section is a nice benchmark. It would be great if every experiment could get there and see that thermal annihilation cross section. The Hawk experiment can only do it in certain special cases. Depending upon the physics of the dark matter, there are scenarios where in today's universe, the annihilation is preferred compared to the annihilation that was happening in the very early universe. If those scenarios are true, then there's certain particle masses, dark matter particle masses, where the Hawk experiment will in fact become just barely sensitive perhaps to the thermal annihilation cross section, which would be exciting, of course. But that's kind of a special case for a particular model. Now again, it is possible that the dark matter annihilation cross-section is up here, and that the dark matter simply just wasn't thermal in the early universe. It was produced through some other mechanism in the early universe. And so this is a worthwhile search to carry out, whether or not they have sensitivity to the thermal cross-section or not. This is a worthwhile search to carry out. The classic example of looking for a dark matter annihilation, I would say, the experiment that's really intended to really answer this question as best we can with today's technology is the Fermi telescope, which is also observing gamma rays. This is a recent publication from them from just last year, where they're searching for dark matter annihilation, looking at nearby dwarf spheroidal galaxies, which are dominated by dark matter. They have very little ordinary matter, and so that would make a clean dark matter annihilation signal if they saw some excess there. They do not, as of yet, see any excess in these neighboring dwarf galaxies, and so they place a limit which is represented by this solid black line as a function of the dark matter particle mass. They place a limit on the cross-section, which is the solid black line. The dashed horizontal line is the thermal cross-section, and this is the fact that their solid black line is below the dashed line is saying that their data is already somewhat inconsistent with the hypothesis that the dark matter particle mass, WIMP mass, is down here around, say, 10 GeV. So they're already sort of disfavoring dark matter masses that are less than 100 GeV in the hypothesis that the dark matter is able to interact with ordinary matter and to annihilate. Okay, so this is one of the hottest topics, I would say, in dark matter physics right now, as to what extent these gamma ray observations can tell us about whether or not it's true that the dark matter does annihilate and that it was thermal in the early universe. Now, our experiment is not a traditional astrophysics experiment in the sense that the Fermi telescope or the Hawke experiment, I would say, is. In our experiment, what we're looking for is we're looking at this diagram of dark matter interacting with ordinary matter, and we're kind of looking at it in this direction. We're going to look for the dark matter to scatter off of ordinary matter. And of course, if it's possible for it to annihilate through some mystery process here, then it should also be possible for us to look in this direction with time going this way, so to speak. It should be true that the dark matter is willing to scatter and able to scatter off of ordinary matter. So that's what we're going to be looking for in our experiment. So what we're looking for is one of the Milky Way's WIMP particles, dark matter WIMP particles, which we believe are present with us here in the room. We're going to look for it to come into our detector and scatter off of one of the nuclei in our detector. So we think of our detector as a target. In our case, it's a target of liquefied xenon. And we're going to be looking for this dark matter particle to scatter off of one of the xenon nuclei in our detector and then leave the detector. What we're actually going to see is the sort of the elastic recoil of that nucleus. We're going to consider that to be the dark matter signature that we're going after. We're looking for sort of anomalous nuclear recoils in our detector that we can't otherwise explain being present. The backgrounds that we're going to be dealing with are mostly of what's called the electron recoil type. These backgrounds are mostly due to ordinary radioactivity of the detector materials, for example. Gamma particles and beta particles that are just from ordinary radioactivity in the detector materials come into our target material, our liquefied xenon, and they, for the most part, scatter off of atomic electrons rather than the nuclei. And so we have lots of events where the where we see these atomic electron recoils. We call those electron recoil events, of course. And this is most of the background events that we're going to want to reject. So we want to build a detector that's able to distinguish a nuclear recoil event from an electron recoil event. That's going to be one of the requirements, one of the goals of our experiment. So this is sort of the parameter space in which we carry out this kind of search. The plot is too complicated. It's showing a whole bunch of results from a whole bunch of different experiments, and I'm not going to attempt to explain it all. And for the most part, you should ignore all that. But mainly what I wanted to point out is this is the parameter space that we're looking at. We don't know the dark matter particle mass, so that's one parameter. And this is a logarithmic plot, so 1 GeV, 10 GeV, 100 GeV, 1,000 GeV, etc. On the y-axis is what this scattering cross-section should be, which we don't know. The annihilation cross-section that I talked about extensively is fixed in the thermal hypothesis. It's fixed by the dark matter density that we see in today's universe, the amount of relic dark matter left over. But when you rotate this diagram this way, if you don't know what's in this mystery circle, knowing the cross-section this way no longer fixes what the cross-section, does not fix what the cross-section is in this direction. If you told me exactly what was in that circle, then I could talk to a theorist friend who would calculate for me what the cross-section that direction translates to in terms of that direction. But given that we don't know exactly what this mystery physics is here, we have to be open-minded about what the cross-section is in this direction. And so that's why we've got this somewhat vast, many orders of magnitude parameter space to search on the y-axis in this WIMP nucleon cross-section space. So experiments that are looking for dark matter the way we are, direct detection, are searching for, and for the most part, ruling out sections of this parameter space. The green, what's highlighted here in green, was the result of our experiment, the Lux experiment, from the result that we published at the end of 2013. So that result's a little bit old. I'll show you the new result a little bit later on. But essentially, because we didn't see any anomalous nuclear recoils in our data at that time, we said, well, the cross-section can't be up here, otherwise we would have seen a whole bunch of events for these various dark matter masses. Okay? So what we're actually, since this is a somewhat traditional nuclear particle physics experiment, what we would like to measure, of course, is sort of the energy spectrum of these recoiling nuclei. That energy spectrum should be a kind of a broad, uniform spectrum because it's an elastic scattering process, and we get all sorts of scattering angles in our data. Therefore, we're going to get sort of all sorts of recoil energies. The typical recoil energy is also going to depend upon the incoming mass of the mass of the incoming dark matter particle, which again we're open-minded about. In general, what we're going to expect to see is sort of exponentially falling recoil spectra. These again are the energies of the recoiling nuclei. and this plot is given in keV. These energies are low from the perspective of a particle physicist. We're talking about tens of keV. In fact, our best place to see it is at the few keV region, because that's where most of the events are going to be. The exact rate that we're going to see events is going to depend upon the target material that we use, and that has to do with the fact that these WIMPs are going to be scattering coherently off of all the nucleons in our nucleus. So in other words, if you use a big nucleus like xenon, the scattering cross section, it goes like the square of the atomic number. So a big nucleus like xenon, which has a typical atomic number of 131, has kind of a boost factor or an enhancement factor compared to a single proton of 131 squared. And that's true for essentially all nuclei. But if you're using neon, which just has fewer nucleons, then the number of events you're going to get, the event rate you're going to get is going to be down by a factor of 10 or more compared to a bigger nucleus like xenon. So this is just explaining, to illustrate one of the reasons why we like to use xenon as a target, is because we're trying to take advantage of this, this coherent scattering process that we think is going to be taking place. So because we're looking at very...
For the bounce, for the shape of these.
This is a form factor. That's some nuclear physics. So the form factor of the xenon nucleus, essentially what this means is that the xenon nucleus is large enough that the scattering is not going to be fully coherent. There is going to be some incoherent portion of it, which is why that this is kind of rolling over and coming back in. It has to do with the structure and scale and size of the xenon nucleus. All of these other atoms, all these other targets would exhibit similar features, but they would be further out in energy.
If it's just size of the nucleus, so why 132, which is probably very rare, really?
Say again, why not 132?
Why use 132, which is probably a rare nucleus, instead of the conventional standard xenon?
So we are using conventional standard xenon. We get the whole mixture of the ordinary isotopes that you find on Earth, and so the average atomic number for xenon it's somewhere between 131 and 132.
I thought it was that one isotope.
No, so I was just saying that's a typical one, but we use all of them, of course. We just purchase commercial xenon, we purify it, and we use it.
Okay.
Yes. So we did not do isotopic enrichment or selection. Okay.
Xenon must be expensive.
It's about $1 per gram, but the price does fluctuate wildly from year to year, depending upon the demand, the market demand.
Yeah.
So there's a whole economics of xenon that we learn more about than we want to know. But yeah, it is fairly expensive stuff. But these other ones are not. Argon is a cheap material because it's so abundant. Obviously, germanium is kind of an expensive thing. So there's trade-offs here.
How do you purify the xenon?
So there's kind of two types of purification that we do. One is to remove ordinary atmospheric gases like oxygen and nitrogen, and that we remove simply with a chemical purifier, with a getter that's able to getter the xenon. The xenon, being a noble gas, is fairly easy to chemically purify in that respect. But we do have to do an additional form of purification, which is to remove trace krypton. Krypton is another noble gas of course, and it's not removed by a getter. But unfortunately, krypton does have a radioactive isotope that would cause backgrounds for us. And so when we receive the xenon from the vendor, we do go through an additional step of purifying it ourselves of krypton. And in the case of our experiment, we use chromatography to do that. Other experiments use distillation. So you need some sort of physical mechanism to separate those two. So
what is chromatography?
Yeah, chromatography is a chemical technique of separating different components of a mixture in different ways, but through some absorbent, basically. In the case of what we're doing, we're using so-called charcoal chromatography, which means we have a big bucket of charcoal, so to speak. We put the xenon in at one end, and the xenon has some krypton, trace krypton in it. Both the xenon and the krypton want to bind to the charcoal surface a little bit, so that it takes it a while to go through the charcoal column. It turns out that xenon wants to bind, being a little bit heavier, its van der Waals force is a little bit more. It wants to bind to the surface a bit more than the krypton, and so it turns out that the krypton impurities will come out the far end first. And so that's how we separate the krypton from the xenon.
You have to use regular, relatively small amounts, because you can't really continually use it. You have to, because
Yes.
krypton will be coming out same time that the xenon is at eventually.
So there's a timing issue. Basically, what we do is the loop there's two loops, and the krypton comes out first. We send that to a krypton dump or a krypton trap. Then when the xenon starts to come out, we switch it and we send the xenon to a different place. And there is some trace krypton that's left over, but you design the charcoal column itself and the flow rates and the pumping rates such that the krypton is mostly sent to the trap and the xenon is fully or entirely sent to the other place. There will be some trace krypton left over at the end, and if you're worried about that, in principle, you can do the process again, but you do have to switch back and forth between these two loops to separate them.
Keep doing it over and over again if have to. That's why they separate bomb uranium from the...
Yeah, but that's expensive again. It's time consuming.
Oh, yes.
It is expensive and time consuming. I mean, in the case of our new experiment, the one we're building now, the budget for this process for removing the krypton is $2.7 million.
Ooh.
So we're going to process 10 tons of xenon for the new experiment, and the budget to do that is $2.7 million.
$1
So the energies that we're talking about, these recoil energies we're talking about, are just a few keV, because most of the events are going to be the very lowest energies. So what we need is a detector, a particle physics or a nuclear physics detector that has an extremely low threshold. The lower your threshold, the better off you are. And in a lot of ways, these direct detection experiments are competing. One of the many aspects they're competing with each other on is their threshold. In the case of our xenon detector, we have extremely low threshold, which is kind of illustrated by this beta decay plot. This is carbon-14 that we purposely injected into our dark matter detector. In order to calibrate the detector, we purposely injected this carbon-14, and we see this classic beta decay shape, which is exactly what Fermi would say a beta decay shape should look like. I included this plot mainly to illustrate our threshold, which is that it's only this very first and second bin here where our threshold is applicable. Everything starting from there is just the true beta decay shape going out to 150 keV. This peak out here is something else that was in the detector at the same time. But our detector threshold is 1.3 keV. And so one way to think about this detector is that it's like an X-ray detector. These are X-ray energies. It's an X-ray detector with a threshold of like 1 keV, except its mass should be as large as possible. A typical X-ray detector that you might use for X-ray astrophysics would be a little piece of silicon, a CCD or something like that. It would be probably a few hundred grams, maybe. At most, when you add them all up, each individual sensor might be less than a gram. But we have many hundreds of kilograms of detector material where we're sensitive in the same sort of keV energy range. So we're going to look for these particle interactions, these nuclear recoils, by looking for the various types of energy that these recoils will deposit in our detector. Basic particle detector physics is that when you have an ionizing interaction in a detector, you can get ionization, you can get light production, and you can get heat. Those are sort of the three options at how that energy can show up in your detector. In our experiment, we don't look for heat, we're not able to, but we do measure the ionization that's produced and the scintillation light that's produced. Those are the two things that we measure, and similar experiments, the other experiments that are out there that are similar to ours are also looking for those two quantities. So this is an animation of how the detector works. This is to illustrate the detector principles. So we have a cylindrical bath of liquefied xenon, which is being illustrated here by the purple. One particular xenon nucleus is highlighted in the middle. We have liquid xenon here. Up above the liquid surface is gaseous xenon. And then we have arrays of photomultiplier tubes that are on the very bottom and the very top. Now, if a WIMP particle comes in and scatters off that xenon nucleus, we're going to make some light, scintillation light, that we'll observe on these photomultiplier tube arrays. But we also make some charge, some ionization, and we set up a vertical electric field to draw that charge up to the liquid surface where it goes into the gas phase. When it gets into the gas phase, it'll be collected by an anode up there. But up there in the gas phase, because the charge is moving faster, it's going to create additional scintillation light up there. And so when that happens, when that charge gets extracted in the gas phase, essentially we get a second pulse of scintillation light that we can see on our photomultiplier tubes, and thereby measure the presence of the charge and measure its magnitude. So essentially what the detector is doing for us is it's measuring both charge and light, but in the case of the charge, it's kind of applying a trick that's turning the charge back into light in some respects. But it's two separate light pulses, so our photomultiplier, so we can identify those in the data, separate them, and measure the charge and light separately. So there's the primary scintillation light. That happens promptly. And then the charge we're going to see later, typically it's going to be about 100 microseconds later, given the drift velocity of this charge. We'll get a second flash of light. And that second flash of light will locate the charge in X and Y. And then also the drift time locates the charge in depth. And so that locates for us three-dimensionally where the interaction was in all three coordinates inside the detector volume. So that's the basic trick. On an event display, it looks something like this. If we plot all of our photomultiplier tubes on this axis here, we have about 120 photomultiplier tubes. And we plot on this axis the time in microseconds. What an event looks like is when we get that first flash of light, we have a handful of photoelectrons that we see from our photomultiplier tube arrays. It's a pretty small signal. We call that S1. That's the prompt scintillation light. Then there's a delay where we're seeing nothing. And then sometime later, the charge gets extracted. We see a much bigger signal. This is representing the charge, and we call that S2. So we measure both the primary scintillation and the charge. S1 and S2 is what we call it. So the basic trick of the experiment, I would say, is to distinguish between, one of the tricks of the experiment is to distinguish between these electron recoil events, which are the garden variety gamma and beta events that you're going to have in any detector that you construct here on Earth, just due to naturally occurring radioactivity. We want to separate out those ordinary radioactivity events, those electron recoil events, from the nuclear recoils, which are much more rare, and which we would like to assign to dark matter interactions if we saw some. So we want to do that particle idea, that separation, and to do that, we make a plot of the ratio of the charge and the light that we're seeing in these events, and we plot that ratio of charge to light as a function of light. And when you do that, electron recoil events fall into kind of a band, and what's shown here is calibration data, where we purposely put in a beta-emitting isotope. We put tritium in fact, into our detector. That tritium is a beta-decaying source, and it makes a nice uniform beta spectrum, and creates these electron recoil events for us, and that allows us to measure where that electron recoil band will be in this parameter space. We measure a similar band for nuclear recoils. In the case of nuclear recoils, we need to use something to substitute for the WIMP particle. In other words, we're trying to calibrate, so we want to know what a nuclear recoil looks like in the detector. So we need to bring in some radioactive source that will make nuclear recoils for us. That means that we bring in a neutron source. So a neutron source will go in, a neutron will go into the detector and scatter off these nuclei, just like a WIMP, in many ways, just like a WIMP particle would. And that calibration data allows us to locate this band of nuclear recoils. They're slightly separated from each other. The red line being the center of the nuclear recoils, the blue line being the center of the electron recoils. So you can see there's this separation. This means that we can reject the electron recoil events by a factor of something like 200 to 500, depending upon the energy that we're talking about. So this means that in our final data set, we're going to get this additional factor of, say, 200 to 500 background rejection from this particle ID that we can do. And that goes back to the fact that we can measure both the charge and the light from these interactions. So here's some pictures of the construction of our detector from about 5 years ago. This is the interior of the detector. This whole volume will be immersed in liquid xenon when we're running. These copper structures that you're seeing here are field rings. They're rings that are setting up this uniform vertical electric field. Up at the top is our grids. It's not visible in this picture, but there's those grids that make the anode arrays, for example, and set up the electric fields. You can see the cathode high voltage cable coming down here, so that's setting the potential on the cathode. And here's some more pictures to illustrate what these photomultiplier tube arrays look like. Again, there's one on bottom and one on top. Here's one of those arrays starting to be populated with some photomultiplier tubes. These tubes are 2 inches in diameter, so that's kind of the typical scale of what one looks like. The experiment is located underground in South Dakota at the Sanford Underground Research Facility, which is historically is the Homestake mine, which is where the Ray Davis Homestake solar neutrino experiment was carried out. In fact, it was carried out in the very cavern that we're in. So the cavern is now named after Ray Davis. It's the Davis Cavern. It's about, like I said, it's about 1 mile underground. So this facility is just a laboratory now. It's no longer an operating gold mine. And this is what that cavern looked like 5 years ago before we moved in the experiment, before we put in the infrastructure, moved in the experiment. So this is the location, the actual location where the chlorine detector was, the solar neutrino detector, if you're familiar with that experiment. It won the Nobel Prize in 2002 or so for having detected solar neutrinos. And some pictures from the dedication of the facility in May of 2012, 4 years ago. Again, showing all of our infrastructure in place. This is the widow of Ray Davis, who was present at the dedication, and she's holding a replica of the Nobel Prize there. That's not our Nobel Prize. That's hers.
Not yet.
We don't have one. Yeah.
Not yet.
And just another picture, kind of showing what the work environment is there. So It's a nice laboratory. You have to wear a helmet, a hard hat, when you are out working in the laboratory, but otherwise it's pretty much like working in any other in any other sort of laboratory, I would say. When you're in the office eating your lunch or looking at the computer, you don't have to have a hard hat on. So that's sort of the work environment. It's a nice place to work.
You have some big fans to control the air supply.
Yeah, so you can see fresh air being brought in here. So yeah, so
Do you have
operating.
nightmares of that going out with power or something?
So there's backup power. So there's various safety systems. Number one, there's 2 power feeds that are coming in from 2 different states at the surface. But if power does go out, there is backup power that will run the air handling while everybody evacuates. In the worst case scenario, if for some reason you're not able to evacuate, there's a refuge location underground that has compressed air, and so that will give you some additional time where you can be underground awaiting rescue. But it's not a dangerous environment, I would say, but you need to be obviously conscious of these risks, and you need to be trained for them, and you need to take them seriously.
And there are living quarters right in that area?
So
With the
we live on the
cafeteria?
surface and we travel underground.
Okay,
How many minutes of air do you have in reserve?
In the refuge, off the top of my head, I don't recall. It's not measured in minutes; it'd be measured in hours or days.
Okay.
And it depends upon how many people there are.
Okay.
There's also banks of purifiers to remove the carbon dioxide that you exhale, of course. So, but yeah, you would have some substantial time in the refuge. But I think the bottom line is that if power went out, there is backup power that will run the air handling while we evacuate the mine. And so that's what would actually happen. I don't expect that we would ever really have to resort to the refuge. But it's there if something really went wrong.
For your serenity.
Yes. In particular, it's really there in case there's some fire that's blocking your path to the egress, blocking your egress path. Some pictures of the experiment. It's suspended inside a water tank, so this whole volume when we're running is filled with water. And there's some additional photomultiplier tubes out here to look for Cherenkov light if cosmic rays go through. I didn't mention this, but we're deep underground because we need to get rid of the cosmic radiation that's present on the surface of the Earth. So that mile of rock is filtering out most of that cosmic radiation, leaving only a tiny fraction of it left. And what's left is tolerable for us.
Same reason Ray Davis was down a mile deep.
That's correct. That's why Ray Davis was underground as well. So in our physics data, we look for we plot the events in this parameter space where we plot the charge over light as a function of the light. The blue curves are telling us the band in which we expect electron recoil events to be present. All the black dots are the actual events we see in our WIMP search data. The red band is indicating where the nuclear recoil events would be. We know that these electron recoil events will spill over into the red band a bit. And so the fact that we see a handful of events down here in the red band is not good. It's not significant evidence for the presence of nuclear recoil events in the data. So in fact, from this data, we set a limit on the presence of nuclear recoils, and that sets a limit on the interacting cross-section of dark matter particles. So we did get some press when when we came up with our very first result in 2013. We got some press. There was an article in the New York Times and some other place. That's a picture of the interior of our detector. And the tone of these headlines is always a bit, sort of ambivalent. Dark matter experiment has detected nothing. I think there's kind of a negative tone there, and I think the
Researchers say proudly.
I think what's being illustrated by this headline is that the journalists are, I think, a little bit puzzled that we've seen nothing, and yet, nevertheless, we seem to be in some ways happy about it. I wouldn't say we're exactly happy, but we feel some pride in the fact that we carried out an experiment. It took 5 or 10 years to mount the experiment. We got the data, we looked for the dark matter. It turns out we don't see any dark matter, and so we rule out some parameter space. So, of course, we take some pride in that whole process. We're happy that the experiment, this experiment was as sensitive as we intended it to be. And so that's why we like to put out a press release. And then I think when the journalists talk to us, they're a little bit puzzled that we're smiling because, of course, we didn't find it. It's true that we would be really excited if we had positive evidence for the dark matter, so they would see us smile even more in that case. But I think that's sort of the issue that's being illustrated in this headline.
You can argue that it's more exciting that you didn't find anything to account for the astronomy results.
Right, so the fact that we see nothing, I think there's a few different possibilities. One is that this whole WIMP model is just wrong, that's not the dark matter. The dark matter is not WIMPs. That's possible. Another possibility that it is WIMPs, but we need a more sensitive detector because the scattering cross-section is still below where we're currently sensitive.
Do you have some kind of calibration that you run or simulate to represent what you might see?
Yeah, so I have a couple of slides here about calibrations in particular, and I can tell you about the WIMP calibration in particular. So to calibrate for WIMPs, we use neutrons. We bring a neutron generator into the lab. You can purchase such a generator, what's called a DD generator. So this generator it does deuteron fusion, and that creates a neutron of known energy. It's 2.5 MeV. We send that neutron into the detector. This cylinder is representing our detector. That neutron goes in, and it causes a xenon nucleus to recoil, and that makes a flash of light. We measure many such neutrons, and that tells us what we expect nuclear recoil events to look like in our data. And so that tells us how to look for the dark matter. Yeah. So the calibrations are, for any experiment, of course, the calibrations are really key to being able to carry out the experiment.
Have you guys been able to rule out the Dama claim of 5 years ago?
Yes. If I go back
And
to the
have
very
they given
beginning.
in?
Pardon me?
And have they given in?
Well, I wouldn't say they've given in. I don't think, you have to talk about it, think about it a little bit.
Oh, there it is, yeah.
Have to be a bit open-minded. So when we plot, there is an experiment known as DAMA, which does have a positive, some sort of positive signal that you can interpret as being WIMP dark matter. The DAMA data prefers interacting cross-sections that are up here, say 10 to the minus 40 or 10 to the minus 41 in these units. We're setting limits that are many orders of magnitude below here. So how do we reconcile these two things? One possibility is that DAMA is not seeing dark matter, but they're seeing something else. Maybe it's some sort of ordinary background that we've not yet accounted for. Maybe they're seeing some other sort of exotic physics, I don't know. But it's difficult to reconcile that result with the fact that we see nothing in the typical WIMP model, and that's what this plot is illustrating. That their result, if interpreted as a typical WIMP candidate, appears inconsistent by many orders of magnitude with what we see in our experiment. And other experiments. We're not the only ones. There are other experiments that are setting similar limits. So it's an outstanding puzzle, exactly what's going on in the DAMA data.
Did you just say a word about what the DAMA experiment is?
Yeah, so it's a sodium iodide detector. It's an array of, it's 100 kilograms or maybe a couple hundred kilograms of sodium iodide crystals. They have photomultipliers, tubes mounted, optically coupled to the crystals. They're located underground in Italy. And so they're measuring the energy spectrum of every event they see in their crystals. They look at very low energies. They look at a few keV region to look for the presence of dark matter interactions. And in particular, they're looking for they can't distinguish between nuclear recoils and electron recoils the way we can. Instead, they're using a different technique. What they're searching for is an annual modulation in the total event rate, which is what you expect if because the Earth is going around the sun, and the sun is going around the center of the galaxy. There's an annual modulation in the typical velocity of the Earth with respect to the dark matter halo. And that causes the cross-section to modulate a little bit. It's a small effect. It's a maybe 5-7% effect. But it should be there if you're looking at cosmological dark matter. If that's what you're seeing, it should be there. So they look for that annual modulation, and in fact, they see it. And they do see an annual modulation, and that annual modulation is what points to these regions of parameter space. So I'm not aware of any good explanation for the DAMA result, either as a WIMP dark matter candidate. This plot is saying that it doesn't look like a typical WIMP candidate, nor as a background. I don't think anybody has a really good explanation as to what kind of background might be causing the effect that they're seeing. So as far as I'm concerned, it's sort of an outstanding mystery of the field about what exactly is going on in the DAMA experiment. Fortunately, there are multiple independent efforts that are now being mounted with sodium iodide itself to try to do a real apples-to-apples reproduction of their experiment. So those experiments should have results in the next 5 to 10 years. And so, we're all quite eager to see if these other experiments, in fact, reproduce the exact same effect. If they do, it'll be very, very interesting.
Is the DAMA result in phase with the motion of the sun?
It does have the correct phase, yes. So one of the things in their favor or in favor of a dark matter interpretation is that it's true that the phase does have the correct one that you would expect for dark matter. Yes.
If they didn't, you wouldn't believe it.
If they didn't, that would certainly be evidence against the dark matter hypothesis. Yeah. Okay, I think let me just wrap up by telling you a little bit about
all those other
our new
experiments
experiment.
are in disagreement with DAMA.
That's correct. Yeah. There was historically, you can see another blue, you can see a blue oblong region here. It's called CDMS Silicon 2013. So in 2013, there was a publication from the CDMS experiment that also sort of, perhaps, it was not terribly statistically significant, much less significant than the DAMA result, but taking it at face value, it preferred this region of parameter space. And again, it doesn't really overlap with the DAMA preferred regions. Some other experiments have had some tentative, possibly positive results, the CRUST experiment. So there's been other experiments that have seen some things in this region, but for the most part, from the perspective of 2016, we think that most of these experiments were probably just statistical fluctuations because they've been ruled out by our experiment and others. I would say the one that remains as really a mystery, as not being a statistical fluctuation, is the DAMA experiment. Their effect is not a statistical fluctuation. So whatever is explaining it, it's not just simply that we got lucky or unlucky in the case of the DAMA experiment. Whereas these other experiments, I think you can interpret that as a statistical fluctuation or some systematic. So we are building a bigger experiment. I mean, we want to go down even lower in cross-section. Maybe we'd like to explore another about 3 or 4 orders of magnitude of cross-section space here. To do that, you need more target material. We're not going to run the experiment for 1,000 times longer than we've already run it. We've already run it for 2-3 years. We're not going to run it for 3,000 years. We need more target material, and so that means getting a bigger experiment. And so this is the experiment that we're building right now. It's called the LZ experiment. We expect to turn it on in 2020. It's going to be inside the same water tank that the LUX experiment is located in the Davis Cavern in South Dakota. That's the water tank that the LUX experiment is currently located in. This is the size of the TPC. It's going to be 10 tons of liquefied xenon. And there's going to be some additional shielding material, some scintillator shielding material. Our cathode high voltage in this case is going to be 50 kilovolts. So everything is bigger. It just means we need more xenon target material in order to be sensitive to smaller and smaller cross sections.
What an expensive xenon.
Yeah, the xenon's about $10 million.
Now,
Yeah, but you don't lose it. You can
We don't
sell
lose it. That's right. So
you can sell it back.
it's an asset, and it's an asset that can in principle be sold back if not used for another science experiment.
as I recall, there were 2 components of the signal. One were the photomultipliers and 2 collected charge above the surface. Does you describe that?
Yes. So there is a charge signal and a light signal, but the charge signal we turn into light, so we detect it as light as well. I can show the event display. So this is the prompt scintillation signal. This is a function of time in microseconds in a single event. We see a prompt signal that's just a handful of photoelectrons, followed by some delay due to the drift of the charge. When the charge gets into the gas phase, it emits lots and lots of scintillation light. And it's that scintillation light that we see. We don't actually read out the charge itself from the anode, although in principle we could. We could put an amplifier on the anode and read the charge directly. Instead, what we do is we look for this scintillation light for a couple of reasons. One reason is that this is a natural amplification process that makes the signal much bigger than it would otherwise be. The signal would be in the noise of almost any typical charge amplifier you can imagine because it's such a small amount of charge. But secondly, it also means we can use the very same detector. That makes the detector somewhat simpler. We use this very same photomultiplier tube to detect both signals. So I think that's all I wanted to say. I think I just have one more illustration of how big the new experiment will be. Tried to place these and scale them to be the same. This is the LUX scale. That's the existing experiment. That's a picture of it over there. So the new experiment, kind of in the same scale, will be about that big. That's the 10 tons compared to, say, the 300 kilograms that we have in LUX.
How important is it to be underground?
Yeah, the detector simply could not operate on the surface. The passage of the cosmic rays through the liquefied xenon is creating enormous amounts of light and charge everywhere. There's activation of the detector materials, so there's going to be short-lived radioactive isotopes that are present with us here on the surface of the Earth. When we go underground, those short-lived isotopes decay away, so they don't make a background underground. So it's completely intolerable to be on the surface of the Earth.
How deep do you have to go?
So we're 1 mile underground, and how deep you have to go is a question of how much residual cosmic rays you can tolerate. In our case, it's reduced by a factor of 10 to the 7, about 10 million, I believe. There's other laboratories that are at different depths, and depending upon the detector technology and how ambitious the experiment is, I suppose, in some sense, you can tolerate different depths for different detectors. So some of the deepest laboratories in the world are in China and also in Canada. Our laboratory is a good depth. It's not the most deep one in the world, but it's perfectly fine for what we're trying to do.
You gotta use what's available. You can't dig a chamber like that.
Yeah, so it'd be too expensive, of course, to dig a laboratory from scratch. That's right. Yes.
Would you comment on that book about dark matter that Lisa said about the Milky Way has a lenticular shape for the dark matter distribution?
Yeah, so we were speaking about this at lunch as well. I've not read the book myself, so I've just heard her speak about it a little bit. So I probably don't know about it as much as somebody who's read the book, certainly. But I guess the hypothesis is that
Lisa Randall.
Yeah, I guess the hypothesis is that the Earth passing through the plane of the Milky Way periodically over geological timescales disturbs the Oort cloud, so we get comet bombardment, and this might be responsible for some of the species extinctions that are seen in the geological record. So I haven't read the book. I'm not an expert on it, but it sounds very interesting.
And it's periodic.
Mm-hmm. The claim is that it's periodic, yeah.
And she claims to see a periodicity in the extinctions.
I think that's the claim,
extinctions.
yeah. I'm not an expert on it, but I think that's the claim, yes.
Yeah.
An issue with the age of the universe is the 13.9 billion years age of the universe. Is that derived from the universe size, the observable universe being 13.9 billion light years in radius? Is that what it's derived from?
For the most part, it comes from the cosmic microwave background. Measuring the size of those 1 degree angular scale spots that we see in the cosmic microwave background, combined with there's a number of different ingredients to go into the argument, but combined with the presence of dark energy, which is also inferable from the cosmic microwave background, and the physics of knowing how long, what physical size, what physical length can collapse once within 380,000 years. Given the plasma physics of an ionized plasma. In other words, what's the scale at which this thing should be in thermal equilibrium with itself? That's setting this 1 degree angular scale. And so all of these things go into the mixture of determining this age of the universe. It's also measurable. Of course, there's other techniques as well using supernovas, the Hubble Space Telescope data from supernova data, as well as decades ago, of course, aging globular clusters, those turn out to be about 10 billion years old as well.
I just figured out that if the universe radius is, say, 13.9 billion light years in radius, that it takes time for the universe to expand to that size, and that if the universe was expanding at the speed of light, which it isn't, that would make the age of the universe 27.8 billion years old at the bare minimum, which gives you a lot more time for these things to happen. But I'm pretty sure the universe is not expanding at that rate of speed.
Well,
at least not recently.
Yeah, so one thing I can say is that, I'm not really a cosmologist myself, but one thing I can say is that the expansion rate of the universe is not really necessarily limited to the speed of light. I mean, in particular, there's this theory of inflation, which possibly took place when the universe was extremely young, 10 to the minus 44 seconds old, where it was expanding at exponentially expanding at a superluminal speed almost. Another thing I would say is that we shouldn't really picture the universe sort of expanding. Maybe this is not what you were saying, but of course the universe is not expanding into existing space. It's space itself that's expanding, right? And so the arguments from special relativity about not moving faster than the speed of light, there really is nothing moving faster than the speed of light, even though the universe is able to expand faster than the speed of light in a theory like inflation, if inflation were true. So I think I probably answered your question, but
Sort of.
yes.
5 or 10 years ago, there were great plans for homestake. Are you sort of on a lesser? That is, how much of the grandiose plans for homestake have been realized or scaled down?
Yeah, so, well, that's a good question. I mean, so our experiment is at the moment, so the plans are very, very much alive. Our experiment is essentially the flagship of that program today. So our experiment is in some sense a culmination of that whole plan, you could say. And at the moment, we're kind of the flagship experiment at that location. there are some other experiments going on there as well. Now, our current experiment, of course, is just wrapping up. We've just taken the detector out, in fact, and we're building this new detector. But looking further down the road, even past 2020, when our new experiment will turn on, there's an enormous neutrino experiment that will be built there to receive a neutrino beam from Fermilab, which is in the Chicago suburbs. So that's $1 billion experiment, including the accelerator we have to build at Fermilab. It's an enormous detector. So the plans from 10 years ago have very much taken hold, and in fact, this is the baseline plan for particle physics in the U.S. So that, in fact, that's sort of the centerpiece of the particle physics program here domestically in the U.S. over the next 10, 20 years will be this neutrino experiment that's taking place at Homestead. Yes?
I was intrigued by your diagram that showed the little neutrino pump near the dark matter curves.
Oh, not on this one, but on a previous?
Yes. And I believe that the neutrino oscillation is evidence of interaction with dark matter. If you have neutrino A oscillating to neutrino B, then if you assume that A plus some other particle X equals B, then X equals B minus A. In my calculations, that has all the characteristics of dark matter.
Okay, that's interesting. Is this the particular plot that you're referring to?
Yes.
It's got this neutrino over here. Yeah.
Yes.
So I can tell you about what's being plotted here. This label says boron 8 neutrinos, and what it's referring to are neutrinos that are created in the center of the sun. So these neutrinos we know exist. In fact, they've been observed by solar neutrino experiments. What this particular plot is attempting to indicate is that if you built a dark matter experiment that was sensitive to this portion of the parameter space, that experiment would start to see these boron 8 neutrinos coming into the detector and causing nuclear recoils. So those nuclear recoil events from those boron 8 neutrinos should absolutely be there. We know the boron 8 neutrinos exist. If you had an experiment that was sensitive in that portion of this parameter space, you should see nuclear recoils from them.
And those oscillate.
So those boron 8 neutrinos, yeah, so solar neutrinos undergo a phenomenon that's very closely related to neutrino oscillation.
And that's that particular.
Yeah, these neutrinos, I mean, the oscillation phenomenon depends upon the energy of the neutrinos, and they're coming out in a broad energy spectrum, so the specific oscillation they undergo depends, changes across the energy spectrum. But what this plot's attempting to show is that if you tried to build a dark matter experiment here, you're going to see events, you're going to see boron 8 solar neutrino events in that detector, and so that's going to limit your ability. You're not going to have a background-free experiment anymore. You'll have a solar neutrino experiment, which is also kind of interesting, but it'll be difficult to look for dark matter given that you'll have a whole bunch of events from solar neutrinos.
No way you're going to shield those.
You're not going to shield those out. The fact of the matter is that nobody has yet reached that sensitivity, although it's possible that we're going to skim it just a bit in our new experiment, the LZ experiment. So it's possible that we're going to see some solar neutrino events, a handful in our next experiment.
Thank you again for a great talk.